Good morning, Mr. B here again, and this is revision lecture number 6 now for EIR 221, which is basically just revising EBN lectures. So we're looking at chapter 5 today, or for this lecture, but only a brief revision of chapter 5 on operational amplifiers. We're not going to go into detail, just the basics of what it is and looking at an inverting and a non-inverting amplifier. Now, I was planning on combining this with chapter 6, capacitors and inductors, but I decided to split the two, so there's going to be a 7th revision lecture that focuses just on chapter 6, capacitors and inductors. So let's get started on operational amplifiers. So what is an operational amplifier, or what we call an op-amp? First of all, it's an active element. What do we mean with an active element? This is in contrast to passive elements that we've looked at so far, inductors, capacitors, and resistors, which require no external power source. An op-amp is active because it actually requires an external power source. So if it comes in a little IC package, so this is a IC package. You can see it's got 8 pins. And why is it an active element? Because it requires a positive power supply, and then it requires a negative power supply, which on the right hand side in the general circuit, you can see where's positive supply, and here is the negative supply going into pin number 4, over here pin number 4 and pin number 7 of the IC. Right, then we've got 2 input pins. There's pin number 2, which is the inverting pin, which is our inverting input. So on this circuit we can actually write a little minus there, and on pin number 3 we have a non-inverting input, also known as, right, let's write a little plus there. So there's our non-inverting input, and then on our output pin, pin number 6, so here we're going to get our this thing, I don't know whether it can write this small, output. Right, so here we've got our output pin. So that's just in terms of why it's an active element. So how does the operational amplifier behave? It behaves like a voltage controlled voltage source. So if we look in here in the equivalent circuit of and please note this is a non-ideal op-amp circuit, we have our 2 input terminals, the inverting input, so the minus over here, we have the non-inverting or positive input at the bottom, and then between these 2 terminals there is a input resistance, Ri, sitting over there. So across this we will have a certain voltage VD. So in this case, what is VD equal to? We can write VD as VD equals, where's the positive terminal? The positive terminal is at V2 minus what voltage is at the negative terminal? V1. So that gives me the differential voltage. The D is for differential. It's also, the operational amplifier is actually also called a differential amplifier because it amplifies this differential voltage. How does it amplify? On the right hand side we then have our voltage controlled, let's write here, let's keep with red, our voltage controlled, so we've got a voltage controlled voltage source on that right hand side with an amplification factor of A times whatever VD is. Then we also have an output resistor which then connects to my output terminal. So what is this output voltage equal to? So this output voltage, if we bring it across, equals, there we go, it's 8 times VD equals 8 times, and we've already discussed what VD is. If we plug in VD into this equation, it's 8 times V2 minus V1. So that's the case for a non-ideal operational amplifier. It's simply behaves as a voltage controlled voltage source. Whatever voltage it sees across the input resistance, it amplifies by a factor of A. But now we're going to make a couple of assumptions for an ideal operational amplifier. So what does ideal mean? First of all, it means that you've got an infinite amplification. We're going to look at the repercussions of these assumptions. So A is infinite. Then we also want Ri to be infinite, and this is going to have certain implications. And then the output resistance there we want to be 0. So how do we analyze this ideal operational amplifier, and what consequences do these assumptions have? So now we're going to look at the slide on what happens if we go from a non-ideal to an ideal operational amplifier. So here's my pen. So now we're going to look at an ideal operational amplifier with these specific 1, 2, and 3 assumptions. What do these assumptions result in? Number one, let's give it a color over here. Number one, let's see, if the input resistance is infinite, it means you can't have any current flowing in either into the inverting terminal or into the non-inverting terminal. Why? Because in here now, let's get a blue wine, because in here we have an infinite resistance. What is an infinite resistance? An infinite resistance is an open circuit, and you can't have current flowing through an open circuit. So I1 must equal I2 must equal 0 amps at all times. I can't have any current flowing into those two terminals. That's number one. Maybe I should have drawn those lines green. Hey, let's make them green quickly. Where is green? So let's make them green. So there, we can't have any current because there's an infinite resistance there. So it's like an open circuit. We can't have any current flowing. All right. I just want to put my little oh, it's still there. Right, the second, now we're going to go to blue. Our second result or consequence of those three assumptions is that because there's no current flowing in there, which means there can't be a voltage drop across that VD, it means that VD is going to be equal to 0, which means V2, V1 must equal V2, which implies that VD equals 0. But now you might ask, wait a minute, but in the previous slide we saw that it needs to amplify this VD, but if VD is 0, then it's amplifying a 0 value, which means the output voltage is going to be 0. But now remember, assumption number one, at the top here, these two in combination, if you have an infinite amplification, then if you amplify and you've got a 0 assumed voltage, then you still have an amplification. Now I know this is a bit mathematical, but we will see how these assumptions actually help us to quickly and easily solve the op-amp. But for now, the important rule is two things. You can't have any currents, number one, no currents going in. In other words, where are we? Okay, so we've got number one over here and number one over there. That's condition number one, or result number one. No currents flowing into the operational amplifier. And consequence number two is V2 must equal V1. Let's now apply these results or consequences into this example of an inverting op-amp. And what we want to find is, we want to find an equation where V out equals some amplification factor of Vi. We are looking for what is that amplification factor over there. Now first of all, let's apply the rules. Rule number one, says that the current that goes in to these two terminals has to be how much? They are 0 amps, so there is no currents flowing in there. Rule number 2 says that V2 must equal V1. So we know that V2 must equal V1. Now look at the circuit diagram. Where is V2 connected? V2 is connected to ground or 0 volts. So if V2 is 0 volts, it means that V1 also has to be 0 volts. So here at node, let's call it node number 1, we have these two equal, and we know that V1 equals 0 volts. Right, so how are we going to solve this? We're actually going to apply Kirchhoff's current law to node number 1. So let's call this node number 1 because it's where V1 is. And now we need two currents. We're going to have one current coming from our source. So we've got one current there coming from VI. And as that current reaches node 1, it can't go into the non-inverting terminal because we know that the current is 0 that goes into the non-inverting terminal. So then the current has to go through RF, which is our feedback resistor. F is for feedback. Why feedback? Because we have the one side of the RF connected to the output, the other side of the resistor connected to the input. So that makes a feedback resistor. So let's call this current I1, and we will call this current flowing here I2. Right, I1 and I2, and we are going to apply Kirchhoff's current law. So we're going to apply KCL at node 1. So what happens? Currents that goes in must equal the current that goes out, which is I2. So how can we write I1 in terms of Ohm's law? So now we're back to Ohm's law. Always Ohm's law. So what is I1? Where does it start? It starts at V1, then it flows to, no, I'm lying, VI, sorry, it starts at VI, then it flows towards V1, and it flows through R1. Right, so that's I1. And that must equal I2. What is I2? I2 flows from V1 and then minus, where does it flow to? The lower voltage, which according to our chosen current direction is V out, and that flows through RF. Right. So remember, what do we want? We want V out as a function of VI. So perhaps you should have written it the other way around, because V out's now on the right hand side. Nah, we'll fix that later. Okay, so let's fix it somewhere now, and we'll bring it across. So what do we know? I just need a different color pen quickly. So what do we know about V1? V1 equals 0, or V1 equals 0 on both sides. So where does that leave us? If we have on the right hand side, if we now bring it across, we've got, in other words, minus V out over RF must equal, and then we bring the other side around, VI over R1. So what did I do here? I just brought this one and that side, and I brought this one to this side. All right. Now we want V out as a function of VI. So now we can write V out must therefore be equal to minus RF over RI times the input voltage. And lo and behold, what do we have over here? This coefficient, this is a constant. So by how much is the input voltage amplified? It's amplified by a factor of minus RF over R1, not Ri. Why did I write Ri? Sorry, Ri1, R1. I still don't like that. It still doesn't look nice. Let's just get rid of it. There we go. R1. Still doesn't look nice, does it? So let's go back to R1. There we go. RF over R1. So that is the simple amplification that we have for an inverting op-amp, which you will be using in one of the pracs if I'm not mistaken. So that's the case for an inverting amplifier. What happens in the case of a non-inverting op-amp? What do we mean with non-inverting? Non-inverting means that when the input is positive, the output will be positive. When the input is negative, the output will be negative. In contrast, the inverting op-amp, if the input is positive, the output will be negative. And if the input is negative, the output is going to be positive. So now we're going to look at a non-inverting input. Now first, again, what are we looking for? We are looking for V out must equal some value of a V I. So again, we are looking for what is that amplification factor. Now notice the difference in this circuit if we're going to, before we apply our two rules, that in this case the source over here, the source VI is now connected to the non-inverting input of the operational amplifier. This is in contrast in the previous case where the source was connected through R1 to the inverting input for the inverting amplifier. Right, so first let's apply our rules. So we know that the current that goes into the op-amp has to equal 0. Yes, there can't be any currents flowing in there. Rule number 2 says that V2 must equal V1. But what are they? In this case, where is V2 connected? V2 over here is connected to the positive terminal of VI. So we know that V2 equals V1 equals VI. Right, this is going to become very important. So right here, V1 equals VI. Right. Now let's again apply Kirchhoff's current law at node 1. We just need to make a node 1 there. So there is our node number 1. Let's write the number 1 over there. There we go. So let's apply Kirchhoff's current law at node 1. Right, what do we get? So the current that goes in must equal the current that comes out. But this time I'm going to be smart. I'm going to write it the other way around. I'm going to say the current that goes out must equal the current that flows in. Same thing. Because I know within I2 is going to be in my V out term, which I want on the left hand side. So what is I2? Where does it start? I2 starts at V1, then it flows towards the output terminal and it flows through RF. Right. That must equal I1. What is I1? Where does it start? Now notice where this current starts, it actually starts from the reference node. So at what voltage does it start? It starts at 0 volts. Then it flows to V1 and it flows through R1. Right, now let's substitute because we know what is V. We know that V1 equals VI, and over here V1 equals VI. So we can rewrite our equation a little bit as VI minus VO, which is flowing through RF, must equal minus VI divided by R1. Now we want to keep V out on the one side, so we're going to write minus V out over RF must equal, we've got this minus VI on that side, and R1 minus VI over RF. Yes, I could have simplified it already, but let's keep the steps small. Right, so let's get rid of the minuses, because now that can become a plus and a plus and a plus over there if we multiply with a minus on both sides. So we can rewrite the equation now as V out equals, so RF comes at the top, RF divide by the sum of R1 and RF, because I'm taking out R1 plus RF times the input voltage. So now I have the A that I was looking for, the amplification factor for a non-inverting amplifier as the feedback resistance divided by the sum of R1 and the feedback resistance. Alright, this is all that you need to know or revise for operational amplifiers for now. I'm not going to do any numerical examples, because that would simply just entail substituting R1 and RF with numerical values, so that's going to be redundant. So what we've done now is what you need. I just want to make one last addition to this equation that we've done. We can actually simplify, what color pen am I at? We can simplify this equation last little bit and just write it as 1 plus RF over R1. So then again, why we would like to do that is, so that again we've got this ratio of RF over R1 like we had for the inverting amplifier, but now it's just 1 plus that ratio of RF over R1 instead of minus RF over R1. Right, so that's it for operational amplifiers. In the next lecture we're going to look at inductors and capacitors.